Hello, and welcome to the first video of section 14.4. In this section, we are discussing the length of curves, or arc length. So in this first video, I actually want to start with a motivating question, motivating example. I'll jump down to my question down here. Now, you may have seen a situation like this before, especially on a hot summer day. You might see a bird, a vulture, or an eagle, or I think hawks do this as well, sort of rising upward in a spiral type pattern, a helical path, right? So what they're doing is they're rising on a thermal, which is this sort of hot air column that's rising upward with respect to the rest of the air. So they're riding on that. And the question I want to ask here is, if we can say track how fast it's going just vertically, if we're just looking at its ascent, how fast it's going vertically, can we surmise how far it's actually traveling? So not just vertically, but what's the length of its path? How fast is it actually going at any moment in time as it follows this helical path up? So in this question, we're going to make some assumptions that it's going 100 feet per minute vertically, and it follows this helical path. So notice this is if you just look at the x and y components, we should see a circle of radius 250. And this would be in feet as well if we're keeping consistent, which we should be. So this is in feet. So 250 feet radius of a circle and then rising upward 100 feet per minute. So if we make these assumptions, how far does it actually travel? Over the course of 10 minutes. And so I do have a little diagram to just kind of go with that. Let me jump to my other scene here. So here is, say, the model, which represents the path of this eagle that's rising on the thermal up into the air. Right? So it's this helical shape. And yeah, our job is to investigate after a certain amount of time how far does it actually travel? So what's the length of this curve? So this extends beyond this one example, right? The same idea extends beyond this. For example, what if this were a thin thing of metal, like a strip of metal, something like that, and we want to take a big, long, like coil of metal, so some length, and we want to coil it up to make it look like a spring like this. So the question would be, how much of that straight metal do we need to then coil up and get into this shape? So like how much material do we actually need to build this? Or maybe this is a model for a staircase that someone wants to build. You need to be able to surmise how much material are we going to need to be able to build up this. So this is all going to be answered by analyzing the arc length of this curve. And of course, this extends beyond helixes, right? We can ask the same question of many other curves. What is the length of this thing as we travel along it? All right. So I'll jump back over here. We're going to end with this example. So let's see. Or actually, rather, this is going to be in the next video. I'm going to work through that example. In the rest of this video, I'll talk through how we're going to go ahead and figure that out in general. So I'm going to ask you to recall, so this is, multivariate calculus. So it's assumed that you've seen arc length before for a parameterized function. Right, so when you had a parameterized function that looked like f of t, or we'll say, so x of t, oops, I don't want green there, I just want white. If you have a parameterized function that looks like x of t, y of t, that you've likely seen before, you might recall that the arc length is given by an integral, we'll say f of t, g of t. So this will be the x function and y function f of t, g of t, that if you integrate, right, square root of f prime plus g prime dt from a to b, you get the length of the arc. So this is something you've likely worked with before. That's in 2 dimensions, but this can be extended very easily to 3 dimensions, and that same derivation from before will work for 3 dimensions, and you get this as the arc length. So it's an integral of this, this. And the thing is, so if we think about this in the context of vectors, what does this represent? So now I'm thinking we have a vector function that looks like this. What does this quantity represent in terms of this vector? Well, it's none other than the length. It's the magnitude of that vector. Right? It's the magnitude of r prime. And so what we're really doing when we're calculating that arc length is we're integrating the speed. Remember that this magnitude of r prime, remember r prime here is is the velocity of the object, or the speed at which you're traveling along the curve, or velocity at which you're traveling along the curve, the tangent vector. If you find the length of that tangent vector, if r is representing position, then this is speed. So I do like to come back to this idea that r is representing position as something. We know the actual vectors are more abstract than that, but it's helpful to have that example. So think of this like velocity, the magnitude of that is speed, and so what we're doing here is we're integrating the speed from between two time values. So this is from t equals a to t equals b. We're integrating that. By the way, this still works with plane curves if we're not in 3 dimensions. We just set the third variable, whatever dimension we're not in, we set that to be 0, and that'll, so for instance, we can plop it all in the xy plane if we're just dealing with a plane curve, so just in the xy plane, and this will still work as well. We just set h of t equal to 0, and the same formula works. So we just use this for the formula for the length of a curve. All right. So right. As I mentioned, it's helpful to come back to this idea of just position and velocity. So more on that. Right, r prime TV, it's the distance traveled, is the arc length. So, right, exactly what I've said before. This is speed. And we're integrating that from t equals a to t equals b. Right, the whole point of this slide, sorry, bear with me. The whole point of this slide is that this is really distance equals rate times time. So rate being the speed of the object, and then multiplying it by time. But we know in a continuous fashion, we know that we can't just multiply. This is not constant. This is changing with respect to time. And so in those situations, we integrate from t equals a to t equals b. So this is our continuous analog of this formula, is this arc length for position. All right. So that's all I want to say about arc length. In the next video, we're going to actually apply this and solve the problem that we set out to solve in this one. See you there.